Thank you, Amber. Thanks for that gracious introduction. And thanks everyone for being here. We got a really interesting topic today, talking about real-time CFD-based bioreactor models with integrated process control. We'll be talking about CFD, some transport physics modeling. We're going to be talking about some controller theory. We're going to be talking about bio growth and cell growth kinetics and how we can incorporate those into these CFD models and whatnot. It's a pretty big tour. I'm excited to hear questions at the end. But we're going to cover a lot of material. So again, chirp up as questions come in. Feel free to put them in the chat. We'll try to get to each of them. I'll go through slides and I'll actually build some models here so we can watch how these things work in real time. And again, everything I'm showing here, I'm happy. All of these slides and whatnot, I'll share with you, as well as any models I use as well. So thanks again for being here. Agenda today. Let me go up to my. It looks like I'm missing my introduction. Okay, that's fine. I can jump right into it. We're talking today about digital twins and digital twins of bioreactors. Now, what digital twin is a word that gets bandied around quite a bit. What I mean by digital twin is a physics-based modeling paradigm for predicting physical outcome. I don't mean a correlation lookup tool. I don't mean just a response surface, as it were. I mean a tool that solves governing equations of transport to make predictions that are indistinguishable from what we measure inside the lab, as it were. And I want to make these predictions, again, at the level of the individual transport carriers. This would be the structure of the eddies. This would be the size distribution of the bubbles and interfacial mass transport. This would be, again, the time evolution of any particles, should there be any particles inside there. And so you kind of think about the hierarchy of modeling frameworks. A lot of engineers tend to work with correlations or some zero-dimensional models. And they're great, and you can classify these as like a digital twin, but realistically, a correlation is algebraically simple, but it masks a lot of the physics. Like here's a familiar Newton number correlation for heat transfer over a sphere. Easy to use, great, but it kind of packages up a lot of the turbulent flow field that's informing why, for example, convection changes with Reynolds number of flow velocity. And so they're useful and fast and easy to apply, but they mask a lot of the physics. A lot of engineers will step down into continue-based representations. I might classify these as RANS type models and whatnot, or more phase field, or I might call population-based models, where we're not tracking individual carriers per se. We're instead describing the net effect of this field, as it were, and how it evolves in space and time in response to certain conservation laws and constitutive relationships. To delve down a bit deeper, we can get closer to actual transport carrier level descriptions. This would be where we're tracking every individual particle in, say, a DEM simulation or a two-phase simulation. This might be classified as more of like a DNS simulation, where the transport carrier can be loosely defined as the eddy, or even something lower where we're looking at molecular transport physics. We're actually modeling the molecules explicitly. But foundationally, these sorts of transport carrier level physics describe present a more holistic description of the system than the assumptions introduced in jumping to a continuum or even to a correlation. And way below all this, we have kind of axiomatic descriptions of matter, like that. Like an axiom that a matter can be described as a traveling wave, and Schrödinger's equation is true. We're not down here. We're not doing DFD or first principle simulations yet at these types of scales. But with advances in GPU computing, we can get closer down to the transport carrier level description. And this has important advantages, because the closer we get down this daisy chain, as it were, and the more physics we resolve explicitly, the easier the models become to build. Said again, the less physics we're captured explicitly, the more we have to kind of patch in with some sort of correlation or some sort of, how should I put this, some sort of coarse graining or subgrid model to capture what's not being resolved by the model explicitly. If you go down to first principles models, there really are no assumptions outside of a level of theory and a basis set. You're just solving Schrödinger's equation. There's no assumption, as it were. As we get up to correlation, there are a lot of assumptions: topology, Reynolds number regime, etc. And so we want to be down here in this kind of daisy chain, as it were, where we have fewer assumptions and more physics. And these advances in GPU-based computing allow us to get there. And here's an example of that, kind of this transport carrier / continuum level description. We're describing the fluid as a continuum. We're using LBM, which is inspired by kinetic theory, to model the fluid mechanics. The DEM particles are modeled as discrete objects. Here we have a few 100,000, nothing too heavy. And at the end of the day, we're modeling these individual DEM interactions, how they're moving through the vessel. We're doing this all in real time, which is enabled by the advances of GPU computing, which allow us to model not just like a snapshot, but a process. So here I have a kind of quasi-continuum transport carrier description of this slurry system. I'm modeling minutes of the process with inline controllers. So again, I have a PID loop informing the impeller speed in a way that minimizes the number of particles stuck on the bottom of the tank. This might be called an NJS, colloquial speaking. But at the end of the day, I'm able to kind of get at this more foundational transport model that has fewer assumptions than, say, a correlation or continuum-based approach, but can run at a speed that is practical within industrial settings and do things and bridge different gaps. In fact, I could use this type of model to develop correlations rather than relying on them exclusively. So what does this mean? It means that when we're building these first principles models, we're really trying to go down this daisy chain to the most foundational transport mechanism relationship we can derive. For fluid mechanics, it means we're solving transient Navier-Stokes. We would prefer to do DNS. At times, we may need to do some LES, but we're not assuming a steady state flow field. We're not assuming mean values, as it were. We're actually watching the turbulent energy cascade evolve organically. If we have to lop off some of the smaller eddies using the LES model, we'll do that. But we're not going to start with some sort of mean flow field assumption and try to start to superimpose physics on top of that. For particle transport, where possible, we're going to try to model every particle. For a lot of bioreactors, this is practical. For fermentation systems, it gets tough. You might need some parcels, as it were, as you get to hundreds of millions of bubbles. But if you've got 10, 20, even 30 million bubbles or even particles, you can model those explicitly. That explicit representation is easier to describe than, say, some sort of correlation-based or parcel. I should say the explicit representation is easier and more general, I'd say, than some of the parcel-based or correlation-based approaches. Species transport, conduction, etc. We're going to do it in line and in tandem. We're going to be solving the advection diffusion equation, right, in tandem with the underlying Navier-Stokes equations to predict the combined effects of fluid flow, chemical reactions. We'll talk about that today, and maybe how those reactions, say, inform viscosity and whatnot. Likewise, for conduction, we try for full 3D. If we need to do some 2D surface-based representations, we may, but generally, we're seeking to describe these models at the level of the most foundational transport physics we can describe. And here are a couple examples. This is just looking at a clean room where, again, this is more PID stuff, where I've got some sort of PID sensor that's measuring the DO concentration. I'm sorry, the gas concentration. And when it gets above a certain value, this kind of purge system, this vent system comes on, trying to remove these excess gases from the room that escaped under the hood. Here is, again, a dissolution process. This is coupled CFD-DEM, where, again, these particles are dissolving over time, which is changing the concentration of the aqueous phase, which is changing its viscosity, as it were, which is changing the EDR, which is forming the bubble or the particle dissolution rate. All these physics are coupled and straightforward to do when I'm describing these physics at the level of the transport carrier. Here's the bioreactors. We'll be talking a lot about these today. I'm just sparging this with dissolved oxygen. In fact, I'll show this movie later. We've got some sparge ring below the impeller, pumping gas in an effort to realize the target DO. And here we're looking at dissolved oxygen concentrations as in the aqueous phase, as well as the Lagrangian bubbles moving through the system. So again, this is our level of theory. And just coming up for air here, this isn't a lookup table. This isn't a steady state solver with a couple like correlations on top of it. This is an attempt to describe physics at the level of the transport carriers in a way that provides a more general and agile solution to these very complex multi-phase, multi-physics processes. This is a heavy slide, but let's jump into the bioreactors now. Within the context of our bioreactor simulations, where we're still making an appeal to this idea of mechanistic transport physics, let's talk about our landscape and how we as engineers think about these systems. Here's a bioreactor, just a little movie of one in case you haven't seen one before. I'm sure everyone here has. But let's think about kind of what the engineer sees, what the chemistry sees, and how we bridge this gap and what we're trying to do here. You know, when I'm designing a bioprocess, as it were, and I've got my controllers, they're watching what's going on, things that I, as the design engineer, can typically control are things like the DO set point, impeller speed, fluid volume, pH set point, etc. I can change the feeding profile, what sort of, glucose, glutamine mixture I'm feeding this vessel, how I'm feeding it over time. This generally is my design landscape, as it were. And maybe you could say like, vessel topology, impeller topology. We'll speak to that momentarily. But at the end of the day, if I buy a bioreactor, these are my degrees of freedom. And at the bottom down here, these are what the cells are demanding, right? These are the cell growth kinetics in terms of their growth rates, their oxygen uptake rates, their production of carbon dioxide. And again, these will be informed by things like the feeding profile, but these kind of are the bookends. What I put in the vessel in terms of the biomass, how I want it to grow, how I'm controlling the vessel, and between these two extrema is where the physics is happening. So I can change the DO set point. I can change the impeller speed, fluid volume, pH set point. And what that informs down below, or what the next layer would be like the actual controller configuration. So if I set the DO point or set the pH value, that's going to inform some sort of controller response. And yes, I may have the wherewithal to change the controller parameterization. Maybe I can change the gain or the reset time, which is all well and good. And so foundationally, but this isn't something that I'm going to be changing all the time. It's easy for an operator to change the fluid volume. It's easy to change the DO set point. Changing the PID controller, that's a next layer of expertise that may not be immediately available to just the operator, as it were. The next layer of sophistication is reactor configuration. This is something that the engineer probably would not change, as it were. The engineer is probably unlikely to change, at least a bioengineer, bioprocess engineer, is probably not going to change the impeller. They're going to buy a vessel off the shelf, and it'll have, especially if it's a single-use bioreactor, some impeller in there. There's some sparge configuration, some microsparge configuration, but that's not really a degree of freedom when designing this process. You control the operating conditions. Maybe you can tune the PID controllers. When you start getting into the topology, you don't change that anymore. That's kind of set by the product that you purchase and the bioreactor you have. There's not really a degree of freedom per se in most single-use bioreactors outside of maybe some variations in the type of impeller at the bottom of the tank. So it's not impossible, but it's less easy to do than just an operating condition. But lower your fluid properties. And I'll maintain this point. Engineers and operators don't set fluid properties. The fluid properties they get are a function or a convolution of their operating conditions and the reactor configuration, and as well the controller configuration. So these, we don't say, oh, I'm going to set the EDR to 50 watts per meter cube. You don't say that. You set an impeller speed. You have a fluid volume, as it were, and you arrive at an EDR. Likewise for the flow rates. These are typically informed by the set point and the controller with respect to any sort of differences that is seen inside the reactor. These guys inform the overall KLA. And I'll reemphasize as we go down this daisy chain. You don't set a KLA. You achieve a KLA by tuning the variables you can control, okay? And so foundationally, when you to tune the KLA, you kind of got to go through this Jacob's ladder of adjusting whether it be the impeller speed, the EDR, as it were, the gas flow rate, etc., which eventually culminates in what the cells are seeing: the DO concentration, the CO2 concentration, nutrient concentration, etc. So all the way up here is what we control, and that's to go kind of through this Plinko daisy chain of all these interlinked reactions that inform what we want to see. And again, I'll kind of harp on that point one more time. We don't set a growth rate. We realize a growth rate as a function of the operating conditions we set. So if we want to maximize a growth rate or tighter expression or tighter yield or whatnot, our way to achieve that is to appropriately tune the operating conditions, maybe the controller logic, as it were, in a way that maximizes this growth down here. And the purpose of the twin here is to link these physics such that if I change the impeller speed, if I change the pH set point, and I know what the controller is, I can then predict from the twin, well, what the fluid properties will be, what the transport physics will be, how that will inform kinetics, and what sort of process yield I'll get. And that's the point of all of this, is to organically capture from operating condition down to cell growth and tighter yield through a mechanistically self-consistent and fully coupled logical daisy chain here. And that's what we're talking about today, is developing these models and incorporate these physics that allow me to go from operating condition to process outcome in the exact same way one would do inside the lab. Let's carry on. We're talking about 3 systems today. We're going to be talking about Amber 250, a 1,000 liter bioreactor, and a 2,000 liter single-use bioreactor. Both these are single-use bioreactors patterned after the XDRs. Some notional properties here. We've got notional fluid levels that are filled to about 80% capacity. We have probes opposite the impeller, which can record things like DO, pH, even inline glucose controls, I'll speak to later. There's typically a single impeller inside these larger subs, as it were. There's a ring spar, or kind of these disc sparges below the impeller. Oftentimes there's a T-sparge as well, which is used to sparge air, maybe carbon dioxide, if we're trying to regulate pH through dissolved CO2. We're going to talk about inline feeding control. And so this isn't necessarily just bolus addition, that is the addition of nutrients to the top. We're going to talk a bit about kind of inline feeding of the system due to some sort of inline measured response. So a lot of our M-Star users have inline, say, glucose measurement, which allows them to dynamically control the feeding rate in a way to realize the target glucose concentration over time. Others do bolus addition. It doesn't matter, but we will consider both. But to be sure, I'm going to lead the way with the idea of inline control, where a probe is recording not only the CO2, or rather the O2, which is forming the sparge rate of oxygen, but as well as the glucose, which is forming the addition of any sort of nutrient to nutrient feed, which again, maybe a bolus addition, maybe continuous addition, but at the end of the day, here's kind of the landscape of the systems we'll be considering here. Average 50, I'll talk about a bit. It's the size of a Campbell soup can, couple impellers, a pretty standard system. An important part of this logic, and this kind of goes down that daisy chain, remember sort of operating conditions, reactor topology, and this inline controller logic. This is a key feature of bioreactors and the simulation I'm trying to build. And in fact, I would say the simulations would be incomplete if they didn't have this coupled physics inside of it. For our purposes today, I'm going to consider two feedback controllers. One, as I mentioned, is a glucose probe, where we're going to have some target value, the set point, some process variable, which is being measured by the probe, which is then informing through controller logic some nutrient flow rate. So again, the control variable is going to be some nutrient flow rate. The set point is the glucose set point, and the process variables was measured at the probe. And the purpose of the logic, the purpose of the controller logic, is to minimize differences between the set point and the process variable. DO is the same way. Our process variable is the DO concentration measured at the DO probe. Our set point is whatever time-varying DO set point we might have. A certain PID controller logic ultimately informs how sparged gas flow rate should vary over time in a way to minimize these differences. Again, I want to reemphasize here that we are going to be incorporating these controller logics into the CFD simulation as well as the biokinetics, as we're going to get this whole coupled picture. I don't mean to go back in time, but guys, I'm marching through this daisy chain, as it were, to develop this coupled simulation that allows me to set the operating conditions, understand the engagement with the controller, and the reactor topology to inform cell growth. So that's really what's driving all this. Just kind of, let's talk about the fluid flow to begin. Momentum transport, modeled using Navier-Stokes. As I mentioned, if I need to use a coarser grid, I'll sprinkle in just a touch of LES filter. That I'm going to be time accurate, though. I want to do DNS, but I want to run fast. So I'll put in just a sprinkle of LES filter, as it were. Species transport, I'm modeling it explicitly as advection diffusion reaction in tandem with the solved in tandem with the momentum transport. So here's kind of what the 2,000 liter vessel looks like. Here's the fluid flow. We'll kind of watch this guy cook. It's interesting to see kind of this the different patterns we get. We are going to get a region of pore mixing in the center here, where there's a torus. I ran two simulations, one with a free surface, one without. I didn't see a huge difference in my KLAs, probably because my vessel was only maybe 1.5 meters deep, as it were, the fluid level. So I chose to ignore the free surface in most of the simulations because of these impeller speeds, which is about 60 RPM. There wasn't much to write home about. I'll play this again. So the velocity feels kind of compelling. Here was some glucose or supplement that I added, just kind of watching that blend over time and kind of watching it follow the contours of the fluid advection field. Again, you'll notice here there's going to be some core, which is the last region to blend. And this will have implications on DO, as I'll speak in a few slides. But again, what I'm trying to reemphasize here is we're solving a transient fluid mechanics simulation. We're coupling that with a transient solution advection diffusion in a way, and these physics are fully coupled. And so that's kind of the takeaway point from this slide. These are my governing equations of transport, and this is the level of fidelity I'm realizing. Bubble dynamics, I'm going to be handling these in a way that we've written about in the previous few papers on a bubble by bubble basis. And I love this approach, and it works great for bioreactors. It gets tough when you get to fermentation systems. You typically do need a particle-based modeling approach because you may have hundreds of millions of bubbles in those types of systems. But if we're below 10 million, as it were, which is, let's say, forgive my loose speaking here, if your KLA is like 50 or lower reciprocal hours, you could probably model every bubble explicitly. And what's neat about these approaches is, again, because they're making an appeal to the mechanistic transport carrier, in this case, individual bubbles, like our breakup and coalescence logic becomes very similar, or I should say simple and self-consistent. We can define breakup as occurring when a bubble enters the region where the EDR overcomes the restorative force of surface tension. We can define coalescence as when two bubbles explicitly tracked come and hit each other. And if they have a critical Reynolds number an approach Reynolds number that exceeds some critical value, they coalesce. And so the advantage, again, of going down to these more foundational transport physics models is that we can have simpler carrier level physics that are agnostic to scale, agnostic to number, as it were, and gets to be applied universally across these different operating conditions. And again, that's the point. This isn't a population balance model. This is with that I dare say it becomes alphabet soup. This is a mechanistic consistent, transport carrier driven breakup and coalescence model that has worked quite well across a number of publications. This is two. I've got a handful of others I can share as needed. And again, the important part is this individual pairwise breakup and coalescence framework. It works across scale because the bubbles don't know or care. When two bubbles are getting ready to break up, or when two bubbles are getting ready to coalesce, or bubbles getting ready to break up, it's not saying, wait, hold up, how big is the reactor? All the bubble knows is what the fluid environment around it is telling it. And so these approaches, inspired by that approach, are agnostic to scale. All they look at is what the physics look like around the bubble and the physics look like between two colliding bubbles to inform the resultant physics, which is a very, I think, scalable and elegant way to look at the problem. And it gets doable because we can model 10 million bubbles. That's a thing. That's not a big deal in M-Star when we're using GPU-based paradigms because, again, we can comfortably model tens of millions of bubbles. And if you can do it, suddenly your modeling approach gets easier. And so in tandem with the PIDs, we've validated this in previous reports. My cover slide is missing for some reason, but I did point to this literature and I can send it to you after the fact, just because I have it here. It was, I don't know why this disappeared, but it was this paper here, should people want to see it. This just came out last fall. This is with BMS and friends. But that's where I'm getting this data here. So in fact, this isn't just a pipe dream. We've actually validated these tools. Like here, for example, and this is before I'm adding the biomass and the reaction kinetics. This is just looking at things like dissolved oxygen and whatnot. But here is like actual laboratory data versus prediction. For this phase 1 here, they kept the impeller speed at 115 RPM, and the set point at 40 RPM. And then here we can see that the black line represents what was measured. Of course, the measured probe was realizing the target value, and the sparge rate was at about maybe 12 liters per minute. Blue is what M-Star was predicting for the measured DO. Green was what M-Star was predicting as well. So at this point here, we're doing a really good job of getting the right answer for the right reason. So again, we were predicting in the code that you need about 12 liters per minute of gas to realize this DO level with this impeller speed, with this background consumption rate going on in the biomass. We nailed it, which is great. And then here they're like, okay, let's do a step change in impeller speed from 115 to 150. And what happens? If we're keeping the set point the same, well, we're going to get more oxygen transfer. We're going to get better utilization of that gas because we're breaking up the bubbles and seeing more EDR. And so for a period, the DO at the probe goes up, and then the system responds by dropping the sparge rate, and eventually it recalibrates back to the set point to 40%, where it was supposed to go, and does so at a lower gas flow rate, which is because the higher impeller speed can make better utility of that gas to realize the target set point. We were a little off here, but it was close enough. At the end of the day, we didn't quite predict the same drop in sparge gas flow rate, which tells me that our KLA prediction was probably like 15% off. That's probably close enough for a lot of these projects because there is some uncertainty in what our KLA is, at least in the simulation and our correlations. But from a process design standpoint, Whether it's 10 or 12, that doesn't matter. The point is it's not 0 or 50. The point is it's something very manageable by the system. Carrying on, the operators then realized a step change in the DO set point. And here again, in response to this, with the impeller speed fixed, the system had to sparge more gas to achieve that higher DO, had to increase KLA. And to get there, it increased the gas flow rate. We see the uptake from the simulation in sparge flow rate. We see the uptake in the measured response versus the predicted response. And this is really cool. Let me reemphasize this point. The simulation correctly predicted how long it would take for the physical system to respond to this change in state. And in terms of the flow rate, it's getting the right answer, the response time, for a pretty good reason, as it were, in terms of what we think the steady state flow rate should be. Last but not least, we drop the impeller speed drop down to 115, keeping the set point constant at 60. Again, if we drop the impeller speed, suddenly the system is not making as much use out of that sparged gas. The bubbles aren't breaking up, they have a lower resonance time, and so the system responds by having to increase the gas flow rate to account for the lower gas utility that it comes to the lower impeller speed. There's a response time associated with this. The spargers have to kick back to some higher value. We did a pretty good job agreeing with that. And the response time of the probe, which is this convolution of KLA, DO consumption, etc., eventually reconverges to the steady state value. And again, the predicted model did a very good job of following the simulation. And I want to reemphasize is we didn't cook the books here. There wasn't like, well, we've got to somehow nudge this reaction time or nudge the PID controllers. The PID settings in the simulation were the exact same PID settings used inside the physical system. Same gain, same reset time, etc. The impeller, the shape, the fluid volume, the cell reaction rates, these are the same things, as it were. We use the exact same PID systems. The weakness in the code is probably the 15 to 20% uncertainty in KLA, which lends itself to maybe a 15% uncertainty in what the exact sparge gas flow rate is going to be. But again, as long as we're getting something that's reasonable, the operator wants to know is going to go to 0, is going to exceed the maximum flow rate of the system. That's the question we can ask, and that's the question we can answer with a high degree of confidence. So this gave us a lot of confidence that this kind of generalized approach of incorporating these physics was valid. And as I mentioned, I can send this off as needed. We talk about this in detail here, where we kind of step through and validate both pH control, DL control, etc. Beyond just reproducing this measured data, we can see inside the vessel and corroborate data that was obtained, but difficult to get. So at each of these phases here, the steady state conditions at phase 1, 2, 3, and 4, I'm presenting a snapshot of the bubble field and the corresponding DO concentration. And what we see here, and this was validated through some specific measurements on these systems, are standing DO gradients across the system. So again, although every system does a great job of realizing the target DO at the probe, 40, 40, 60, 60, that doesn't mean that the DO across the vessel will be equivalent to that probe value. Here we see gradients in the 20s, as it were. Here we see, percents in the 20s. Here we see percents in the 40s. In fact, there seems to be the standing 20% difference between the target DO and the DO realized at the top of the tank. This is very consistent with what was measured experimentally. When we predicted it, they put a probe in there and then they measured it. So it's neat to see the idea that this physics predicted from the code, which was initially anticipated, this magnitude, was that it corroborated. That as we got this overall global response, then be able to peer inside the tank and see the net effect of this response, the net effect of this dynamic system on potential gradients across the vessel and how that might inform cell growth. That was a big deal. And again, why does this happen? Well, because these processes with ongoing consumption, as it were, are more like a conduction than a convection physics. Yeah, I get it. The mass transport around each bubble is convective, purely convective, as it were. Within the context of this within the context of the broth, we're going to have all these bubbles, which are not going to be uniformly distributed across the system, with a KLA that is not uniform across the system, transmitting oxygen to the aqueous phase. We're going to have uniform DO consumption rate, most likely, as it were, but that non-uniform DO transfer is going to lead to non-uniform DO distribution across the vessel and a standing gradient at that. Okay, now let's jump into these cell growth kinetics, because everything I've shown so far has only included kind of a background consumption of oxygen, a background production of CO2. We haven't yet modeled any of the cell growth going on underneath the hood. We can do that. Let's jump into that. We're modeling all these physics in space and time. Let's go after it. And here's where we need some sort of empirical insight. That is, we need someone to give us a cell growth model. I'll reemphasize, M-Star is not used to predict a cell growth model. M-Star is used to predict the effects of that cell growth model in tandem with operating conditions on fluid flow on process yield in terms of titer or biomass. And so there are these in the literature, or a lot of, I'd say, a good biopharmaceutical companies can develop these, right? They can look at their cell growth kinetics, understand the sensitivity to feeding, and develop these relationships. But at the end of the day, this is what these kind of look like. You have some sort of cell growth that's informed by growth rate and death rate. You have a glucose, glutamine, which are being consumed as nutrients. We have lactate and ammonia that are being produced as part of the respiration. We have titer, as it were. These are all coupled. The growth rate informs, and the biomass informs the instantaneous rate of change in glucose and glutamine. They inform lactate and ammonia. Titer is pretty passive. It's just kind of growing in accordance with the amount of biomass. None of these functions are tied back to titer, at least in this formalism. And we can see some familiar trends here. The biomass has a growth rate, and then we try to have a maintenance phase. We see, in this case, glucose, it was a pretty simple feeding profile, where it was held constant for about the first half of the process, then jumped down to about half the or quarter the initial value. Glutamine's coming along for the ride as it comes as part of this glutamine. This glutamine's one amino acid in this nutrient that is dominated by glucose. Ammonia, lactate, they're doing their thing too. But again, this is generally what this landscape looks like. And we want to be able to incorporate these multi-day reaction kinetics into M-Star. We want to be able to link operating conditions, fluid flow, controllers, cell growth kinetics within the context of one kind of model to rule them all. So that's kind of, I kind of redriving these guys, so I'm kind of giving these guys some names. I'm not listing all of the parameters, but I'm highlighting some of the key ones here. Biomass, growth rate, death rate, these are then more convoluted functions of glucose and glutamine concentrations. Those are what are determined by the biologist, as it were. What the engineer has is some sort of supplement feed rate and the concentrations of glucose and glutamine inside those concentrations, inside those feed lines. And so these first terms here are just generalized reaction kinetics that the biologist comes up with. This is where the engineer starts to play. The engineer starts to say, okay, if we're going to be adding, this feed line with this concentration of glucose, if I'm going to be adding this feed line with this concentration of glutamine, this is where we as engineers start to design and nudge and squeeze, as it were, some of this time evolution of X to B. And in fact, this is quite apparent. And here's some illustrations of this. Here I'm showing cell growth, lactate, and ammonia production in response to different combinations of glucose and glutamine. So in each of these cases here, I'm kind of dynamically feeding glucose and glutamine in a way that achieve these kind of target concentrations. And we can see there are differences in particularly cell growth. Look at these blue dots here, which correspond to a maintained glutamine concentration of 7 millimole with different glucose concentrations. We're not seeing a huge variation in glucose, and that's not unsurprising given the glucose half rate. We can speak about that later. But as we go to different glutamine concentrations, we see that this process depends strongly on glutamine concentration. If I have too little, I'm going to get a lot of growth, as it were. We're going to produce a lot of lactate, which is going to accelerate death during the maintenance phase. If I have too much glutamine, again, I'm not going to get enough growth, as it were, during the growth phase, and I'll have good maintenance, but I'll be suboptimal in terms of my final VCD. If I have kind of this Goldilocks situation of the right amount of glutamine, as achieved by appropriately tuning my feeding strategy and my concentration, I can maximize cell density throughout the maintenance phase. And what I'm trying to illustrate, guys, here is that these are engineering degrees of freedom. These are not. These are outside of maybe temperature. Generally speaking, the reaction kinetics are informed by the cells. But these guys here, the rate at which you're feeding and the type we're feeding, can perturb these dynamics in a way that allow us to maximize cell growth and titer yield at process end. And that's what we're going to be focusing on, at least from a design standpoint. And if I go back to that flow chart, I had feed profile in blue. That's this. This is what we get to select. A couple of numerical considerations before we go into this. And I apologize if I'm geeking out, but this is a subtle but important point. If we just stare at some of these parameters and think about putting them into a CFD model, there are some red flags that should go up. I'm dealing with very, very large floating point numbers here. So again, cell densities are measured in billions of cells per liter. Growth rates are measured in 10 to the minus 6 reciprocal seconds, as it were. So if I'm just doing math, if I just simply think about some sort of like time stepping here, where I want to know what the concentration of biomass is going to be at my next time step, given my previous time step and my growth rate times my delta T, as it were. It's simple, just first order Eulerian, just humor me, as it were. But there's a point here. We're going to be trying to add a number that's 10 to the 9. We're going to try to add to that number close to 1. So this growth rate will be around 10 to the 3. Our time step to do the simulation is going to be like 10 to the minus 3. We're going to have a problem. Okay. Instead, again, we want to run a single precision because we want to be able to run the simulation for days, as it were. But we're not going to be able to track variations that are 9 orders of magnitude smaller than the values which are being added, as it were. In fact, you can even include IOManip and change the number of variables, the number of significant figures here. It won't change the result. Like if I take 10 to the minus 9, add 1 to it, I get 10 to the 9. And if I take a difference, I get 0. The computer can't even see this, as it were. And so we're going to think about incorporating these physics into a CFD solver that's being built for speed. And it's going to have an explicit time step linked to fluid mechanics. We're going to have to think of some sort of numerical scale in here. First, we're going to do non-dimensionalization. And the way I did it is I just non-dimensionalized all species concentrations by the initial value. Non-dimensionalization is safe. It's not a problem. Non-dimensionalization just allows us to operate in numbers near 1, which is where floating point precision likes to live, as it were. So non-dimensionalization, this is not new. This is routine in numerical simulation, where we attempt to take numbers that are very large, which might lead to rounding errors in a computer, and have them operate near floating point logic that is much closer to 1. So we can get away from this 10 to the 9 nonsense by using non-dimensional variables. And again, in the manuscript that we're writing, we list these all one by one. And if you want to talk offline, I will show you how to non-dimensionalize these reaction kinetics. This is not a hard process. But at the end of the day, what you get here is some non-dimensional growth rate versus some period, right? Like time is, everything's non-dimensionalized. And so that helps us with this kind of the floating point arithmetic, but it does introduce this idea of some sort of period. And here's where I have to make an engineering assumption. Non-dimensionalization is fine. That's not a problem. But I do have to make an engineering assumption here to try to make this a bit more tractable. You know, I still have this 10 to the 9 difference in timescales. I have my simulation time step, which is millisecond. I have bubble breakup, impeller, RPM, eddy lifetimes. I've got bubble resonance times, blend times, which are tens of seconds, PID reset time, 100 seconds. And then 1, 2, 3, 4, like 5 orders of magnitude slower, I have my reaction and process time scale. So again, these are minutes, these are days, as it were. And so one approach here, an approach I'm going to validate as I move through this, is to say, you know what? Let's accelerate these reactions. Let's pretend this period isn't 14 days, but maybe it's 14 hours, as it were. Or maybe it's 28 hours. Some time scale that is very, 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 very long compared to these intrinsic physics, as it were, the PID controllers, the blend ends, etc. That's still like so close to infinity that all of these fluid mechanics and the PID response don't care that the cell process is happening in 2 days as opposed to 14. And I think there's actually some ground I can stand on. Like if we're designing a PID controller and looking at how, flow physics and informing process outcomes, 2 days is still infinity compared to a 30-second blend time or a 3-minute reset time, as it were. So whether it's a 2-day or a 10-day process, those reaction kinetics are so slow compared to our underlying fluid mechanics and control system dynamics that they don't really care, as it were. And so as a numerical trick, and I'll justify this in a bit, I may be able to exploit this non-dimensionalization to model a 14-day process as a 2-day process. And the gain is that my simulation runtime is 7 times faster. Okay. So again, I'm going to justify this momentarily, but I want to emphasize that point, is that I don't need reaction scaling. I could, in principle, do everything double precision and just let it run for 14 days. But if I want to make this industrial tractable, I'm going to want to run in single. And I'm going to want to find a way to make a 14-day process like a 2 or even a 1-day process. Because even a 2 or 1-day process in terms of cell growth is infinity compared to blend time, reset time, etc. I'll come back to this and validate it momentarily. So here's what this looks like. And for some reason, this is easier to show on YouTube than embedded into PowerPoint. This is a busy slide. So I'm going to show this a few times. Okay, look at the left here first, and look at the right. Viable cell density, local DO percent. As the viable cell density goes up, and you see these colors change here as the viable cell density grows over this multi-day process, it's going to increase the oxygen demands. So viable cell density is going up, oxygen consumption is going up. In response to those increased oxygen demands, the sparge rate, shown here in these black bubbles, must increase. Said again, as VCD goes up and those cells sort of gobble, gobble, gobble more and more oxygen, the controller kicks on. So the probe is always reaching its 40%, as it were, but in order to get that, the controller logic had to go back and increase the gas flow rate in a manner that increased KLA to make the OTR match the OUR at the set value of 40%. And note, here it comes again. We see standing gradients inside the DO concentration, just like we saw in the BMS paper, as it were, just as they measured, as it were. Just because the probe says, oh, hey, all's good, we got 40% DO at our point here, that doesn't mean that there may not be very low DO zones somewhere inside these last to mixed regions, as we saw earlier in the simulation. Sorry the quality isn't great. I'll send the YouTube link if you want to see it. But at the end of the day, we can see here how the growing viable cell density on the right causes the number of bubbles to increase in time. And this increasing OUR stresses the OTR in a way that produces oxygen gradients across the system during the maintenance phase. Okay, which is pretty interesting. Let's look at the glucose here. Here we're seeing something like a daily bolus addition. Let's look at the glucose here as it goes on. We're seeing this kind of spike of glucose as the glucose at the concentration at the probe goes below the target value. The PID responds by adding glucose to the system. So here we're seeing this coupling as well. Again, time and time again. And this glucose homogenization is very fast, but for this kind of semi-bolus, I was doing kind of I had a PID controller with a pretty loose gain, so kind of waited a while to add. Then when I added, I kind of hit it hard. But either way, so it's not a perfect bolus addition, but it's representative of something pretty close to daily addition. But at the end of the day, we see it again here. The probe is doing great. The probe is seeing pretty good glucose concentrations. But the dynamic feeding process, the finite blend times, as it were, the controller response times, as it were, does lead to periodic fluctuations in glucose concentration across the vessel. And this can introduce problems, as it were, with wasteful respiration and inappropriate protein expression, for example, in the high glucose regions. But again, this is how these physics come together. What I've got here is fluid flow. I've got here multi-phase flow. I've got controller logic. And I have, importantly, the time evolution of the VCD. And so kind of marching on through what I get, let me see if I can go on to the next slide. Okay, I can see, for example, familiar things. Like here is viable cell density and glutamine going over time. So initially I've got, again, I model this as a 1.4-day process. So again, I use an acceleration factor of 10. But because everything is non-dimensional, I can then scale that to a 14 process. So I'm claiming 14 days. I modeled 1.4. My next slide will show why I think it's okay to do that. I don't think I could model this as a 1-hour process, cell growth process, because at that point, the cell growth kinetics would have time scales comparable to the PID controllers and blend time, and that'd be really weird. But in as much as my biogrowth process is in days, I'm on good legs to stand on when I'm exploiting my non-dimensionalization. But here again, we see, despite these kind of complex feeding and growth profiles, we're seeing pretty homogeneous cell growth, as it were, and a nice throughout the maintenance phase, and this all looks well and good. But again, this is an important point, is that I'm modeling the cell growth physics in tandem with the fluid flow, in tandem with the controller, in tandem with all of these multi-phase physics as well. Let's take a peek here at glucose control. I ran the system again with a more appropriate gain parameter, as it were. And here I can see, this is my target glucose level. This is the glucose concentration over time that maximized cell growth. And here was how the system responded. Like as cell growth is going up, is trying to feed more and more and more glucose into the system in a way that keeps the concentration constant at the probe. And again, as cell growth is maximized, as cell growth goes up, it's squeezing as much glucose as it can. The controller system is really pumping glucose in. Eventually, it starts to go into the maintenance phase. That glucose feed rate goes down. We have a more benign injection rate, as it were, and less variations in the vessel across space and time. But again, this had a different gain, but that's kind of the point, is I can actually use this framework to assess a different PID parameterizations and whatnot might inform the controller response, the glucose feed rate, and the potential variations in concentration and their effect on cell growth. Like it's all coupled, as it were, with this level of fidelity. This works well across scales. So we've done this again in the 250, 1,000, 2,000 liter. And this goes back to the first point I made. When we're building models based on transport physics carriers, as it were, those models become scale independent. Okay, remember, I wasn't using some KLA response surface. I was modeling multi-phase physics at the level of the individual bubbles and transport carriers. As a consequence, whether it's an Amber 250, an XTR 1000, XTR 2000, or a 10,000 liter vessel, those physics don't change. Likewise, the cell growth kinetics don't change. They don't. The cells aren't looking around and saying, "Oh, how big is our land?" They operate in response to glucose, glutamine, and other nutrients, and so those physics don't change. And so the model I developed for one conveys to all scales, and I can run it across again 2,000, 1,000, 250, as it were, and show, okay, as you get to smaller volumes, you get a little less variation in, say, glucose concentration. You get very similar feeding characteristics for this well described PID controller system, and that's because it's the same reaction kinetics in each cell, or rather at each scale. But importantly, is if I built model at one scale, I can use it at all my scales to assess how scale up might inform cell growth, dead zones, mixing, PID parameterization, etc. And here I'll show again how the growth kinetics change with scale and tau. And I promise I'd do this. These black points here, these represent the exact solutions with no time scaling. I'm modeling a 14-day process, as it were. These lines here represent the predictions from the solver at different scales with different time scales. So even with tau's up to like 56, which means like almost like a 12-hour process, even in those systems, the 12-hour process is still slow compared to the 20-second blend time that is close enough to infinity to represent the well-stirred non-scaled system, as it were. And so it really seems to corroborate that I do have a degree of freedom here to make these simulations run faster. And again, and making them run faster by shortening, or rather accelerating, the time at which these cells grow. And again, I can see this numerical trick. We're actually just magically making these cells do their thing 10 times faster, as it were, 14 times faster. But the savings to us is the code can run in 2 days as opposed to 30, right? If we can take advantage of these scalings, and apparently with no loss in fidelity. And again, just to reemphasize this point, beyond just looking at cell growth, beyond looking at operating conditions, I can tune feedback control or whatnot. And here is me looking at different gain settings, different sorts of reset times, as it were, and seeing, okay, if I come away with this gain, if I come in with this reset, I can identify a controller logic that minimizes the error between the set point and the realized value. And that's neat because I can design this process, the feeding schedule, the controllers, etc., the operating conditions, the controller response times, purely in silico, from nothing more than the vessel topology and the reaction kinetics. And that's very compelling. Okay, let's kind of go with some conclusions. I'll then show the model, and we'll try to have a few minutes for time. You can always email us. We're always here to talk about this stuff. And I imagine some people's questions might be very specific. We can go into deep dive. We can model the standard stuff. The headline isn't good news, everybody. We can model mixing. It's not a headline. Or good news, everybody. We can do KLA. That's not a headline. Okay, we can do it very well, and it's working quite well, but that's kind of standard stuff. The headline one is good news, guys. We can do CFD now in tandem with auxiliary control system dynamics, pH, nutrient, oxygen control, etc. And begin to see the coupling between those control dynamics, operating conditions, and culture environments, as it were. The second headline is good news, guys. Beyond just doing the controller systems and kind of like speculating on what the cells are going to do, we can model the cells and how they grow, how they evolve in space and time. We can model I would say the evolution of the viable cell density and titer production as a function of the feeding schedule, which is informed by the PID, which is also driven by the operating conditions. All these physics are coupled, as it were, within the context of one holistic model. It's practical to simulate days of process time per day of wall time. So again, I can comfortably simulate the growth phase, in a day. I need to use time scaling, make it maybe like a 14 or 28. So I need to accelerate that process a bit. But generally speaking, it's still infinity compared to the operating conditions and vessel time scales. And we can validate that. We can do it even on a case-by-case basis by looking at different towels to convince ourselves there is no sensitivity. And there will be a sensitivity. Obviously, if we make the reaction kinetics all happen in 2 minutes, it'd be nonsense. You'd have this wonky system. But foundationally, if you're sensible with your time scaling, you can recover very fast run times, as it were, with no material loss of fidelity. And again, it's everything I'm showing here. These ran in 2 days to do 14 days, as it were. So it's focused on just like a growth phase or whatnot. I could do that in a day. We could do that in a day on a good GPU. The fully coupled model can be used to optimize feeding profiles and scale campaigns. And importantly, it provides a mechanistic link between the operating conditions, the growth kinetics, and process yield. That big flow chart I showed is all encapsulated in this type of model. And we can see bell to bell, head to tail, how the operating conditions inform the physics that ultimately lead to reactor response, culture environment, and cell growth. And that's pretty cool. I have a closing slide, but I'm just going to go real quick just so people can see. I've got 1 minute or so. If people want to see and play with this model, I'm more than happy to share some of these key components. Let me go ahead and find it real fast. Just 1 second here. I should have had it up, but I kind of restarted my computer because I didn't want to have any sort of here we go. I didn't want to have any sort of competition for my resources. So here it is. Again, I know we're at time, but I'll just kind of give those who use M-Star a peek behind the veil. Familiar old vessel wall impeller bubbles. DO, here are my reacting species, O2, glucose, glutamine, lactate, ammonia, BCD. Here are my cell growth reactions, right? They're all kind of non-dimensionalized. I do all my math in non-dimensional ways. But these guys, those are what I showed in the paper. Those are what were published by others. These are the familiar cell growth kinetics, as it were. Here I have my logic, my PID for the DO. I have a set point. I have a gain and a reset time, as it were. We have some sort of, target DO, probe DO, and sparge flow rate. Glucose PID. We've got the same logic here. There are a lot of parameters. These cell growth kinetics, there's, probably 20 of them. Now, this isn't a numerical, excuse. It just takes a lot to parameterize the reaction kinetics. And here they are, the cutoffs, the half growth rate constants, the maintenance coefficients, etc. They've got to be specified. And so I just keep them in tabular form and then evoke them down here within my reaction kinetics. And at the end of the day, what I get out of this is exactly what I showed you. I get out of this thing all the physics. And again, this is my last thing I'll show before kind of opening up for a few minutes of questions. What I get out of it is that familiar M-Star output, the time evolution of the flow field, the time evolution of the velocity, the time evolution of the glucose concentrations. This is, here we go. There's my time evolution of my viable cell density, looking at timing stats where I'm claiming to get about 2 days for, I can run a full process in about 2.5 days. That would be 21,000 seconds for this. This is a pretty aggressive acceleration, but it all comes out in standard M-Star form. Guys, we're at time. We covered a lot, as it were. Thank you for being here. Thank you for kind of coming through this kind of broad tour of operating conditions, fluid mechanics, cell growth kinetics, optimization, PID controllers. This we covered a lot. I'm happy to take any questions. We got a few minutes now, and shoot me an email. I'm easy to find. LinkedIn, email, you got this. We're easy to find. Shoot us an email. We can talk in detail. Happy to talk about any level of theory here, be it the transport physics modeled in the fluid, be it the reaction kinetics, be it non-dimensionalization, acceleration, be it controller logic, be it validation, etc. Happy to talk. Everything I know, I'm happy to share with you. Look at our literature. If some of this is new to you, we published on this a lot. And keep your eye out for upcoming work on some of this bioprocess integration. We spoke about it last fall, ASHG with Pfizer. Look for a paper, hopefully soon, from the same cast of characters. Amber, I'll turn it back to you. Should we have a few minutes for questions? But yeah, thank you again for giving me a chance to speak. And I'm happy to field any questions folks have.
Yeah, there are a few questions, although it looks like some of them maybe have been answered, but we'll just start. In order to accelerate the growth rate, you change both the reaction kinetics and the reactor volume? That's the question.
No. In order to accelerate, the reaction kinetics are informed by reaction volume. The cells don't care how big the vessel is, at least in the way I'm approaching the system. In order to accelerate the reaction kinetics, I am non-dimensionalizing the dynamics, as it were, and using a dimensionless time scale that is greater than 1 second per second, as it were. I'm saying that like 14 seconds of modeled time, 1 second of modeled time corresponds to 14 seconds of physical time, as it were. And so the vessel scale is not accelerating the dynamics, as it were. The non-dimensionalization is accelerating the dynamics. If I didn't answer that well, call me and we'll talk through it in detail.
All right, there's one other question that I think maybe hasn't been addressed yet. It is, what would the limitation be on how fast you can accelerate a simulation? Would it be the controller feedback time?
I think yes. Going back to this slide here, we've got to make sure we are decoupling these timescales here. We've got to make sure that we're not intruding these process timescales into these reset timescales. And so I would have a very hard time convincing myself to have a process that was shorter than like 6 hours. Even that's kind of 6-hour process, pretty fast. You're kind of getting close to that response time of the PID controllers. But if we're at like a day, as it were, or even like 12 hours, 16 hours, then you're pretty safely decoupled from those faster timescale physics. Great question.
Okay, well, that wraps it up. Thank you so much, John. Thank you for your presentation today. Thanks to all of you who've come to take time out of your day to join us. And I just want to inform all of our viewers that this webinar has been recorded and you will be able to access it soon through a link on our website. And like John said, reach out if you have any additional questions.
Thank you, guys. Appreciate your time.